Okay, so we formed our carbon-carbon bond in this example, and we have generated the start for our aldol product. Now, to complete this aldol reaction and to get our neutral isolable product, what will happen next? So if we want to get the neutral beta hydroxy ketone product, well, if we're quenching this reaction, so during the quench step, if we quench this reaction with mild acid or with water, that in turn will give us our desired beta hydroxy ketone product. Sure, that's more than reasonable to propose. So we've isolated our desired aldol product formed by the reaction of cyclopentanone with benzaldehyde. So this student proposed mechanism looks completely reasonable. Does anyone have any questions on this student proposed mechanism? Or are there any questions on the general mechanism for the aldol reaction? Any questions I can address before we move on? If not, yes, there are no other products because our starting material is symmetrical. You do get a mixture of diastereomers at these two positions, but the stereochemistry of the aldol reaction is saved for future upper division organic courses. Okay, so let's keep going now, and let's talk about a key feature of the aldol reaction. The aldol reaction is reversible, favoring the condensation product only for aldehydes with a single alpha substituent. With di-substituted aldehydes or ketones, steric factors and the steric strain in our aldol product is quite significant. Thus, for this aldol reaction, the equilibrium favors the reactants when you have hindered substrates, such as substituted aldehydes or ketones. So for example, for cyclohexanone, even though it can undergo the aldol reaction and we can form this carbon-carbon bond, this aldol product is not favored heavily at equilibrium. Does this idea that the aldol reaction is reversible make sense to everyone? So because the aldol reaction is reversible, when we think about the aldol product that we're generating, if the aldol product that we make is highly strained and we have excess acid or base floating around, we can undergo retroaldol reactions to reform our reactant. The aldol reaction is reversible under acidic and basic conditions. And as a result, when you have hindered ketones or aldehydes, the aldol reaction, this initial addition step, favors the reactants in many cases. Does that discussion make sense? Okay. Now, just because this initial addition step is reversible, and just because in many cases the aldol reaction, this initial addition step that we'll call from now on the aldol reaction, is an equilibrium that in many cases favors the reactants, Removal of water from the aldol reaction mixture can be used to drive the reaction towards the products. Even if the initial aldol reaction favors reactants, the subsequent dehydration step pushes the reaction to completion to form your desired enone product. And we'll call these products aldol condensation / dehydration products. So the way that this works is by Le Chatelier's principle, looking at this equilibrium currently, this reaction is reversible because you can deprotonate this oxygen and break this carbon-to-carbon bond. If you dehydrate and remove water, then you have removed water from the product side of this second equilibrium, and as a result, the equilibrium will respond to the change in the concentration of water by generating additional product and generating additional water as a reaction product. So by removing water, we're able to shift this equilibrium all the way to the product side and generate a significant amount of our desired enone product. So does this idea that even though the aldol reaction is reversible, the fact we can drive this reaction and drive the equilibrium towards the products via dehydration and removal of water? Does that idea make sense to everyone? Okay, so let's talk a little bit about some mechanisms. Let's talk about the quote unquote retroaldol reaction. Let's show why this reaction is reversible and how this reaction is reversible. And then let's talk a little bit about what's happening in this second dehydration step. So for your retroaldol reaction, suppose we have this aldol product. So we have our desired aldol product. How is this aldol reaction reversible? Well, if we have any excess base floating around, we can deprotonate our alcohol and make an alkoxide ion. The best way that I can describe this alkoxide ion is think of it very similar to the alkoxide generated as part of carbonyl addition reactions. And as we've learned in carbonyl addition reactions, if we can reform this carbonyl by losing a leaving group, we can often lose our leaving group. So in this case, this entire ketone compound or enolate can be thought of as a leaving group. And so when we kick down to reform our carbonyl, we can lose an equivalent of enolate. So we reform our desired carbonyl and we lose our enolate, which is our reasonable leaving group. Similar to how, for example, you can kick down a cyanohydrin and lose cyanide. It's the same idea. We can reform our carbonyl by losing a leaving group. And in this case, our leaving group is an enolate. Does this explain to everyone why the aldol reaction is reversible if you have excess acid or excess base floating around? Does that make sense to everyone? Does this retroaldol reaction make sense? Okay, and just as a reminder, let's refresh ourselves on the two main cases where retroaldol is favored. So it's favored when what? So what are our two cases? You can use equilibrium arrows, but in this case, the retroaldol reaction heavily favors this desired retroaldol product. So why and when is the retroaldol favored? It's based on our electrophile. And for what substrates is the retroaldol product favored? When our electrophile is what? So going back to our earlier discussion of the retroaldol process, when is the retroaldol product favored? So looking, we saw when we have substituted, specifically disubstituted aldehydes or ketones, then the retroaldol product is favored. So let's write that down. This retroaldol reaction and this retroaldol product is favorable when the electrophile is a disubstituted aldehyde or ketone. That's the first criteria. And two, when excess acid or base is present. Does this idea of the retroaldol reaction make sense? Okay, so let's talk about how we can dehydrate these aldol products to drive the equilibrium towards the desired enone and the desired aldol condensation product. So beta hydroxycarbonyl products from your aldol reaction can be dehydrated to yield conjugated enones. The term condensation refers to the net loss of water and the combination of two molecules. This dehydration can occur either under acidic or basic conditions. And I'd just like you to note that this dehydration is relatively exothermic. You're forming a quite stable carbon-carbon double bond as well as an oxygen-hydrogen single bond. So if you compare the bond enthalpies for the bonds that you're breaking and the bonds that you're forming in this dehydration step, you'll notice that the net process is relatively exothermic, just looking at the bond enthalpies involved. Most commonly, dehydration is accomplished with the addition of acid and or heat, with the caveat that in many cases, if the dehydration is slow or not permitted, you can see retroaldol reactions occur. So the most common way you dehydrate these beta hydroxyketones or aldehydes is under acidic conditions with a little bit of heat. Alternatively, the dehydrations can be accomplished under basic conditions, especially if your substrate's activated. Does this idea of dehydration of beta hydroxyketones to prepare enones and to drive this aldol equilibrium towards the desired product, does this make sense to everyone? So now what we're going to do is we're going to talk about the mechanism for the acid catalyzed and the base catalyzed dehydration. So under basic conditions, if we have an excess of base, such as hydroxide floating around, then we can dehydrate via first deprotonation of our acidic alpha proton to generate an enolate. From here, this very much reminds me of an E1CB reaction where we've generated a stable anion, and then that anion is used to eliminate our leaving group, which in this case, our leaving group is hydroxide. This is favored in this case because we are generating a very stable carbon-carbon bond. We're reforming our carbonyl, and the loss of hydroxide is favored via entropy as well. So this is the textbook E1CB elimination mechanism. We generate our enolate, and then we lose our leaving group, which is hydroxide. Does this mechanism for base catalyzed dehydration make sense to everyone? Okay, so let's talk about the acid catalyzed mechanism. So in this case, we're first going to activate our leaving group. So rather than kicking out hydroxide under basic conditions, we are going to protonate our alcohol and generate the substantially better leaving group of water. Okay, from here now, we can tautomerize our ketone to the corresponding enol tautomer. So from here, now that we have our enol tautomer set up, we're ready again to kick out our activated leaving group, water. Again, very reminiscent of the E1CB mechanism for elimination. From here, we just have one more cleanup step where we deprotonate our carbonyl oxygen, and that gives us our desired enone product. Does this mechanism for the acid catalyzed dehydration of a beta hydroxyketone make sense? Any questions on this mechanism before we move on? Okay, so when you think about the acid catalyzed aldol reaction, so after our initial aldol reaction to generate the beta hydroxyketone, the final dehydration step to complete the aldol condensation can be thought of as functioning either two major mechanisms, a direct E2 mechanism or an E1CB or 1,4 like elimination. Both mechanisms are viable to draw. I just wanted to share with you that there are many ways to draw this last dehydration step. Okay, so let's move on now. And let's try to apply what we've learned to the following example. So in this case, we're asked to predict the product from the following reaction and draw a mechanism for the following reaction. So in this case, we're treating the following beta hydroxyketone compound with hydrochloric acid and heat. Let's try to predict the product from this reaction and then draw a mechanism to justify why we observe our predicted product. So as we work through this example, I'd love for students to share their proposed responses in the chat, verbally, or annotated directly onto the class whiteboard. And as we work through this example, if there are any questions that I can address, don't be shy to ask them in the chat or verbally. So we have this beta hydroxyketone, we treat it with acid. What product are we going to see, and what's the first thing that's going to happen? What thoughts do we have so far? What do we think? So we're definitely going to make an enone product, and if we treat our basic beta hydroxyketone with acid, we will protonate our alcohol, and that in turn activates our leaving group. Rather than kicking out hydroxide, now we're ready to begin to kick out a leaving group such as water. So from here, now that we've protonated our alcohol, we can now tautomerize this ketone to the enol tautomer. From here, now that we have the enol tautomer, we can kick out our leaving group and generate our desired enol. Answer the question in the chat. All these recordings are saved and posted on Canvas as well. And the annotated notes will be up if the file is readable after processing. Okay, so we kick out our leaving group, which is water, and we generate our desired enone. We would typically see a mixture of alkene stereoisomers. In this case, generally, you would prefer to generate the least hindered alkene. So you'd want to place your alkyl groups trans to each other if possible. So this student proposed mechanism looks completely reasonable. So let me clear these annotations and let's just redraw this mechanism for our reference. So we have this beta hydroxyketone and we're treating it with strong acids such as hydrochloric acid. The first thing that's going to happen is we're going to protonate our basic functional group. From here, we've now activated our leaving group via protonation. For our next step, we're going to tautomerize our ketone to the enol tautomer. And from here, we're now ready to kick out our leaving group, which is water, via elimination. You can think of it like a 1,4 elimination, almost the exact opposite of a conjugate addition reaction. From here now, as our last cleanup step, all we have to do is deprotonate our carbonyl oxygen to get our neutral isolable enone product. Generally, from these dehydration reactions, we'd expect to see a mixture of products with the transalkene being the major product. And that's just because in this elimination, you'd prefer to eliminate to generate the least hindered alkene if possible. I can scroll up, yeah. Any questions on this reaction? Any questions on this problem? Okay, so let's try to apply what we've learned and put the two pieces together for the aldol reaction and the dehydration step to complete the aldol condensation together. So let's try to predict the products from the following reaction and draw a mechanism to justify our predicted products. So in this case, we are taking a ketone and treating it with sodium hydroxide. And just to be clear, we can say 0.5 equivalents. Substoichiometric sodium hydroxide. Though the same reaction would work with one equivalent of sodium hydroxide, just because sodium hydroxide is a very weak base, and thus we only see a little bit of deprotonation to give the enolate. Okay, so let's try to predict the product from each step of this reaction sequence, and let's try to draw a mechanism to justify our predicted product. We've seen the mechanism for the aldol reaction, and we've seen the mechanism for the dehydration of beta hydroxyketones to the corresponding enol. Let's put those two mechanistic steps together, and let's put these two concepts together, and let's try to draw a full mechanism for the aldol condensation and dehydration for this compound. So would anyone like to share a photo or annotation of their proposed mechanism? We have one student commenting, do we first see deprotonation of the most acidic alpha proton? Yes. Would you be able to show that deprotonation step on the class whiteboard? We have another student predicting the following enone product. Yeah, so we have students predicting the following enone product. And that predicted product looks reasonable, but let's try to draw a mechanism to justify our predicted product. So we have an acidic alpha proton. So I see many students commenting in the chat that we can deprotonate that alpha position to generate an enolate. And because we're using sodium hydroxide, which is a relatively weak base, we'd see a very small amount of this enolate generated. But it doesn't take much of this enolate in order for you to see aldol reaction products. So once we have this enolate is nucleophilic and can attack electrophilic species such as our ketone or aldehyde. So in this case, our nucleophilic enolate will attack our electrophilic ketone to generate our aldol product. Let me clear that annotation and just redraw that step so everyone's able to see. So we have our electrophilic ketone, which is attacked by our nucleophilic enolate. So from here, we get our aldol product. And this is really important. Is this initial aldol product favored at equilibrium? So if we made this aldol product, would it be easy for us to isolate this beta hydroxy compound? Would it be easy or difficult for us to isolate this beta hydroxy compound? It would be relatively difficult. If we're not careful, especially because we have excess sodium hydroxide floating around, we'd expect to see some retroaldol processes. And that's just because this ketone is relatively hindered, and so our aldol product after addition is relatively hindered. It's not impossible, but it's still quite difficult for you to isolate a lot of the beta hydroxy product. You'd see a relatively reduced yield just due to retroaldol reactions. However, if we quench this reaction, and we quench this reaction with strong acid and heat, or if we take the isolated beta hydroxy ketone product and treat it with strong acid and heat, what will happen next? So we add the hydrochloric acid, and in this case, we wouldn't need heat because this alcohol is benzylic. What will happen when we add acid to this compound? So treatment with acid will protonate our alkoxide ion. If we have excess acid floating around, what's going to happen next? So we have this beta hydroxyketone. We're treating it with excess acid. How are we going to drive this equilibrium towards the products? This beta hydroxyketone can be isolated in low yield, but usually in order to drive this equilibrium towards the products, we dehydrate this beta hydroxyketone to the corresponding enone. So how would we complete this dehydration reaction? How can we activate this hydroxy group as a leaving group? Yep, we'll protonate our alcohol to activate it as a leaving group. So let's show those steps. So we first protonated our alkoxide to quench that basic species. And as we still have excess acid floating around, we can protonate this alcohol again to activate it as a leaving group. Water is a much better leaving group than hydroxide. Now, we have this protonated, highly substituted benzylic alcohol. So would it be easy or difficult for us to eliminate this alcohol? Is it relatively easy or difficult to eliminate this benzylic alcohol? Quite easy, right? So we can just eliminate this equivalent of water via textbook, almost E2-like elimination. And that in turn gives us the predicted and desired trans enone product. Generally, if you have a preference between forming two alkenes, the least hindered trans alkene is preferred. Does this mechanism make sense to everyone? And does this example of an aldol condensation reaction make sense? Wonderful. Okay, so when we talk about symmetrical aldol condensation, such as the aldol condensation we observed in the previous example, symmetrical aldol condensations work best when you have a small amount of base used to generate a small amount of enolate in the presence of unreacted carbonyl compound. After condensation, your basic catalyst can be regenerated. And in this case, because we're using a relatively unhindered aldehyde, you can actually isolate this beta hydroxyaldehyde quite easily. One thing I'd like to comment is even though the aldol reaction is reversible, you still can isolate the beta hydroxy product for many reactions. It's just a matter of choosing your conditions such that there is not a large amount of excess acid or base floating around in your reaction mixture, because that's really what sets off your retroaldol reaction. So does this discussion of symmetrical aldol reactions make sense to everyone? Okay. So from here, we're going to talk a little bit about mixed aldol reactions. So a mixed aldol reaction between two similar aldehyde or ketone partners tends to lead to a mixture of 4 possible products. So it's not the most synthetically useful reaction without careful control of the reaction conditions. So if the enolate is not pre-generated, a mixture of aldol products are typically observed. Further, proton transfer reactions between the generated enolate and the other ketone or aldehyde leads to undesired mixed aldol side reactions. So there are 2 things that you have to be concerned with. First is the matter of enolate generation. So if you have a ketone and you have an aldehyde, you always have to be worried about which proton your base will choose to remove. Generally, the aldehyde proton is more acidic, so the aldehyde would be preferentially deprotonated. However, if the pKa difference is less than 3, you'd see a mixture of enolates generated. The solution to this is to pre-generate the enolate. So for example, you take your desired ketone, you treat it with base, you make your enolate, and then, and only then, do you add your electrophile. So if you pre-generate your enolate, you can sidestep these issues. The second issue is the issue of proton transfers. So suppose you have the following ketone, you make this enolate. This ketone has a pKa of around 22. So you make your enolate and you think everything is going to be fine. Okay, I'm just going to add my electrophile and this reaction will work great. However, if you add an electrophile that looks like this, not an unreasonable electrophile, and if you just look at this alpha position for a moment, this alpha position would have a pKa of around 10. So would you see an aldol reaction in this case, or would we see proton transfer? What is more acidic, our parent ketone or this aldehyde? This is really important. What is more acidic? Would this enolate be the preferred enolate? No, we're going to easily transfer a proton and generate a new, potentially undesired enolate. So it's important when you're planning out an aldol reaction that you consider the pKa of both your parent ketone that you're using to generate your enolate and your electrophile's pKa value. If there is a difference greater than 5, you're likely to see competing proton transfer and undesired mixed enolate products. So there's no straightforward way to engineer away this proton transfer issue. Instead, you just have to be careful in choosing your substrates. And whenever you propose an aldol reaction, just check the pKa values to make sure there's not a huge difference in acidity. Because if there is, your enolate may not function as an enolate and may instead function as a base. Does this make sense? Does this discussion of mixed aldol reactions and ways to control mixed aldol reactions make sense? Okay, so from here, let's talk about some other examples of practical mixed aldols. First, we can use an electrophilic ketone or aldehyde that lacks acidic alpha protons. If one of the carbonyl partners contains no alpha hydrogens and you can't form an enolate, and the carbonyl is unhindered, it is a great electrophile for aldol condensations. We also have something that's very interesting to think about. When we think about this aldol reaction, so we have two potential sites to react, alpha and alpha 1. We only see reaction at one of our alpha positions. Now, it's important to note in 2-methyl cyclohexanone, it is the only substrate in this reaction mixture where we can actually pull off a proton. That allows us to generate an enolate, which from there can attack our electrophile, which in this case is benzaldehyde. Wonderful. So this gives us our beta hydroxy ketone. And let's think about for a moment why we only see one aldol product. Why do we see only one aldol condensation product? This is a very important idea. So if we think about our two possible aldol products via reaction at position alpha or alpha 1, why is only one of these aldol reactions productive? When we look at this alpha, we see that we can easily eliminate an equivalent of either hydroxide or water, right? What about alpha 1? Can alpha 1 eliminate hydroxide? Can we push this equilibrium to completion? No, it cannot eliminate. Thus, looking at this condensation product, although we can isolate we can potentially isolate some of this aldol condensation product, we often see a lot of retroaldol. If you can't eliminate and lose hydroxide or water to make your enone, oftentimes, because this aldol reaction is reversible, it will funnel towards the reaction pathway to give your enone. So, for practical mixed aldols, we choose our substrate, 1, so only one of our substrates has enolizable protons, and 2, because the aldol reaction is often driven to completion by a dehydration step or loss of hydroxide or water to form your enone, you can get regioselectivity because the dehydration step drives the reaction to completion. If one of your sites cannot actually eliminate an equivalent of water or hydroxide because it lacks an available proton for this elimination step, you will often see retroaldol and funneling to a single regioisomer. Does that discussion make sense to everyone? It's a subtle thing, but it's important that we explain it and we talk about it together. as this can help explain and help us understand why, for many aldol reactions, we can observe a single regioisomer after elimination. The other way that you can really load the dice and make one aldol product preferred is by using a carbonyl that has a much more acidic alpha proton that you can readily and preferentially generate an enolate from. Ethyl acetoacetate, for example, is quite acidic. This alpha proton has a pKa of around 11 to 13, and thus it is completely converted to its enolate ion under weakly basic conditions, at least compared to the normal carbonyl compounds, which have a pKa of around 20. Thus, for example, aldol condensations with ethyl acetoacetate occur preferentially to give the desired mixed aldol product. And the reason why this works is if you have ethyl acetoacetate, for example, you're going to preferentially form the enolate of ethyl acetoacetate because this alpha proton's more acidic. And once we make this enolate, we won't see any competing proton transfer reactions. So this enolate can then go and attack our electrophilic ketone carbonyl to generate our aldol product. Because enolate generation is quantitative, we don't ever see a lot of self-condensation with ethyl acetoacetate. Further, just to skip one step, would anyone like to comment on this elimination step? Why is this elimination relatively easy? So when you have these activated substrates, such as, for example, the beta hydroxyketone formed from ethyl acetoacetate, for example, why does this elimination happen without any added acid? Why is this elimination so favored? What makes this elimination faster than normal? So if the elimination is driven by a deprotonation step under basic conditions, would we expect this deprotonation and elimination to be fast or slow? Just in general, in broad terms. If we have this alpha position, and in order to eliminate hydroxide, we need to deprotonate the alpha position. Would this deprotonation step and the subsequent elimination be faster or slower when we have this ethyl acetoacetate? We have many students commenting ethyl acetoacetate is highly acidic. It's easy to pull off this alpha proton. So then, would we expect this elimination to be relatively fast or slow? Fast, exactly. Does this idea and do these tools for practical mixed aldol reactions make sense to everyone? Perfect. Okay, so let's try to apply what we've learned here, and let's try to predict the product from the following reaction and draw a mechanism for each step in the reaction. So in this case, we're treating this ketone with sodium ethoxide and formaldehyde. And what trick are we using in this case? What trick are we using to ensure that we only get a single product? What trick are we using here? Does formaldehyde have any enolizable protons? Can formaldehyde form an enolate? No, exactly right. Okay, so given that, if we treat this ketone with sodium ethoxide and formaldehyde, what product will we observe from the first step? And then after we quench this reaction with hydrochloric acid and heat, what final product will we observe? So let's work through this example over the next 4 to 5 minutes. And then I'd like students to share their proposed responses as photos of their written work in the chat. You can share your responses verbally, or you can annotate your responses onto the class whiteboard. So, would anyone like to share their proposed mechanism, or would anyone like to share their initial thoughts? So we treat this ketone with sodium ethoxide, which is a base. What's the first thing that's going to happen? What's the first thing that we're going to see happen in this mechanism? So what will happen if we have a carbonyl, a ketone, with an acidic alpha position? When you say ethoxide attacks the carbonyl, would you be able to draw what you're trying to convey? Would you be able to draw that out on the whiteboard? Is ethoxide going to attack our carbonyl, or will it deprotonate our ketone? What does the class think? Yeah, we're likely going to deprotonate the alpha position. Exactly right. So which alpha position? Well, only one alpha position is available, right? The other position is completely substituted. So we generate our desired enolate. And from here, what happens next? We generate our enolate, we add formaldehyde. What happens next? So we've generated a nucleophilic enolate. We have the electrophile, which is formaldehyde, floating around in our reaction mixture. So what will happen next? Yep, our enolate, which is nucleophilic at our alpha carbon, will attack our electrophilic formaldehyde aldehyde carbonyl carbon. That in turn gives us our aldol product. Okay. So what happens then now that we take this aldol product and we treat it with acid. What's going to happen next? Would anyone like to continue on with this mechanism and try to complete the next few steps of this mechanism? So we have this beta hydroxyketone. We treat with acid. So we'll see protonation. We'll then further protonate our alcohol to further activate it as a leaving group. So after protonation, now that we have activated this leaving group in the form of water, what will happen next? Now that we've activated this leaving group in the form of water, what will happen next? Elimination, exactly right. We'll pull off our alpha proton and eliminate an equivalent of water. That in turn will give us our desired enone product. Though I would note that under the reaction conditions, this particular enone may isomerize. Does this mechanism make sense to everyone? The student proposed mechanisms that I saw in the chat and the explanation for each step in this mechanism that students have shared as we work through this problem were perfectly reasonable. Any questions on this example before we move on? Okay, so let's keep going now and let's try to predict the product from the following reaction and then draw a mechanism for each step in the reaction. So this time we're taking ethyl acetoacetate and we're treating it with sodium ethoxide followed by acetone. And what is the trick that we're using in this case? What trick are we using in this case? So we have this beta ketoester. What's so special about this beta ketoester? The beta ketoester is more acidic. So if we have two alpha positions that I'll call alpha and alpha prime, which position is preferentially deprotonated? So for the beta ketoester, if we treat it with base, which position is going to get deprotonated? The alpha position, right? This alpha prime position is less acidic, and as a result, we wouldn't see a significant amount of deprotonation. Okay, so with that in mind, let's try to take what we've learned and let's apply each of the steps we've learned for the Aldol reaction and dehydration. And let's try to draw up the full mechanism for this reaction and predict the products from this reaction. So as the students are beginning to annotate, first, ethoxide will deprotonate our highly acidic alpha proton. From here, we'll generate the corresponding enolate. From here, our enolate will attack the electrophilic acetone carbonyl carbon, and that generates our beta hydroxyketone product. One thing that I'd like us to note is you actually don't need the hydrochloric acid for this substrate. Would you be able to draw out the mechanism under basic conditions, given that this beta ketoester substrate is so activated? We can actually see elimination easily under the basic reaction conditions. In fact, it's pretty hard to isolate the beta hydroxy product because the elimination step occurs so rapidly. So we have our alkoxide, we've generated a little bit of ethanol. So what's going to happen to this compound if there's a little bit of ethanol floating around? So here we're looking at the elimination under basic conditions. So we are going to protonate this alkoxide ion, except rather than using hydrochloric acid, we're going to use ethanol or another equivalent of substrate. Would you be able to show that protonation step? So you've made some ethanol, right? So rather than protonating with hydrochloric acid, just show the protonation with ethanol. Yep. So now we have our beta hydroxyketone. And we previously commented that these activated substrates, such as beta ketoesters, can eliminate readily under basic conditions. So we'll be able to draw our beta hydroxyketone and show that elimination step. So from our beta hydroxyketone, you're correct that if we were under traditional acidic conditions, we'd protonate our alcohol. But under basic conditions, rather than losing water, we can just lose hydroxide. Would you be able to show the mechanism for how we can eliminate hydroxide under basic conditions? So we're not going through water as a leaving group. Under basic conditions, we can actually just kick out hydroxide. So we still have base floating around. We have this acidic alpha proton. So we still have plenty of ethoxide floating around. So if we have more ethoxide floating around, we can pull off our alpha proton and lose hydroxide. Except our base in this case probably is not going to be water, but an equivalent of ethoxide. Yep, exactly. Perfect. So these student proposed mechanisms looked great. So let's just reiterate the key steps. I wanted us to talk about both an acidic and basic elimination mechanism in these examples, because for these more activated substrates, you will often see elimination occur readily under basic conditions. So as we talked about, beta ketoesters are useful substrates because they can be preferentially and quantitatively deprotonated under relatively mildly basic conditions. So we can use weak bases such as ethoxide to deprotonate the alpha position selectively and generate our enolate. From here, our enolate can attack the carbonyl carbon and generate our desired beta hydroxyketone precursor. From here, we've made a little bit of ethanol, so we can regenerate our basic catalyst. The aldol reaction can be run catalytic in base or stoichiometric in base, depending on whether if you want equilibrium or quantitative enolate formation, and whether you want a thermodynamic or kinetic enolate. From here, as the students have shared, we can deprotonate our alpha position and then eliminate hydroxide, and that gives us our desired enone product. This occurs readily because the beta ketoester alpha position is highly activated. Does this mechanism make sense to everyone? Any questions on this example? Okay, so let's keep going then. And let's talk about an application of the Aldol reaction, which are intramolecular aldol reactions. So treatment of dicarbonyl compounds with base produces cyclic products via an intramolecular reaction. Now you may say, where am I going to get these dicarbonyls? Where are some ways that we can generate a dicarbonyl? What's an easy substrate to use to generate a dicarbonyl? What's a common reaction that makes a set of ketones, aldehydes, or carboxylic acids? What's a common reaction that makes these kinds of dicarbonyl functionalities? Ozonolysis, exactly right. So ozonolysis is often a common method to prepare these 1,4-diketones or other diketones. And these diketones can then be subjected to aldol reaction conditions to generate substituted cyclic enones. Does this general idea that intramolecular aldol reactions can be used to prepare cyclic enones, does that idea make sense to everyone? This is an important pattern recognition sequence. If you see a cyclic enone, you may want to think intramolecular aldol. Does that idea make sense? Okay, let's talk about some subtleties of this reaction. So we know that there are multiple alpha positions, right? We can call them alpha and alpha prime once again. And although both of these alpha positions can be deprotonated, in practice, what we see is that only one of these positions gives a productive product. Is only one of these reaction pathways is actually productive. So for example, if we pull off this alpha proton and we generate the aldol product, we have a 5-membered ring. If we pull off the alpha prime proton, our proton B, and we try to make our aldol reaction happen, we see that we get a 3-membered ring product. Generally, when we think about ring strain, which of these two ring sizes is preferred? Which of these two ring sizes is favored? The 5-membered ring or the 3-membered ring? 5, yeah. The 3-membered ring is too strained. Further, this elimination step is very difficult. A cyclopropene ring system is a highly strained ring system that's very difficult to form. So thus, even though we can go and we can deprotonate either of our alpha positions, in practice, only one of our positions reacts productively. And that's why we only generally see one condensation product from these intramolecular aldol reactions. Does this idea make sense to everyone? Is everyone comfortable with this example? Okay, so then let's try to apply what we've learned and let's try to predict the product from the following reaction and draw a mechanism for each reaction. And this will be the last example for tonight's lecture block. So let's try to finish strong and let's try to predict the product from this reaction and then draw a mechanism for this intramolecular aldol condensation. So let's work on this example over the next 4 to 5 minutes. And if there are any questions I can address, don't be shy to ask them in the chat or verbally, and I'd be happy to provide input and guidance as we work through this example. Let me read the chat. Can I draw the hydrogens? Sure. Did that help? So we have this carbonyl compound. We have multiple acidic alpha positions. Which alpha position leads to a productive reaction? So I like to draw some dotted lines and just count my ring size. So this would be a 3-membered ring. This would be a 5-membered ring. This would be a 3-membered ring. Of our choices, we know 5-membered rings are preferred. So then we'd pull off the alpha position that would give the 5-membered ring. So we deprotonate our alpha position and we generate our enolate. Let's not skip a step, but you are on the right track. Let's just show the first deprotonation step. Let's just show our enolate. You are correct that we'd eventually see condensation, but let's just show once we deprotonate that alpha position, that gives us an enolate. From here, now that we've generated this ketone-derived enolate, that enolate is nucleophilic. Would you be able to draw the enolate out explicitly? So ethanol is not attacking the alpha position, it's just deprotonating. So we've removed this proton and we're generating an enolate, which is a carbon-centered anion at this alpha position. No worries. So let's just draw where we're at so far. So we have our substrate. We concluded that only one of our alpha positions would lead to a productive reaction. So we're going to deprotonate our alpha position and generate our enolate. So from here, now that we've generated our enolate, what happens next? No worries. So now that we're all on the same page, now that we have our generated enolate, are there any electrophiles that can react with our enolate? So hydrochloric acid doesn't come into play just yet. We still have to do our key carbon-carbon bond forming event. So we have our enolate, which is nucleophilic. We have an electrophile, which is an aldehyde. So our enolate can attack the electrophilic aldehyde intramolecularly. Yep, exactly right. And that gives us our beta hydroxy compound. Yep, the proposed mechanism, the arrows drawn look great. And one thing to note is that this intramolecular reaction is highly favored because it's intramolecular rather than inter. So your nucleophile and electrophile are held in close proximity. So even though the Aldol reaction is reversible, you have greater chances of seeing a condensation reaction occurring. Would you be able to draw the product from this condensation step? I like to draw a dotted line between my two carbons to help me make sense of what bonds I'm forming in this reaction. So from here, now that we have our beta hydroxy ketone, if we quench this product with hydrochloric acid and we heat our mixture, what will happen next? So let me just re-annotate what the students have drawn so far. One moment. So we have our beta hydroxy ketone. So would we be able to show how we get our enone product? Since currently this reaction is still relatively reversible. So how do we drive this reaction to completion and get our isolable enone product? Would anyone like to take this mechanism from here? So we protonate our alcohol sequentially. So we protonate once to give an alcohol, we protonate a second time to activate our alcohol as a protonated leaving group, such as water. From here, we can then kick out our leaving group via almost like an E2 elimination pathway.
Would it be, or what would we be using to do that?
You can use water. As hydrochloric acid, it's pretty difficult to generate anhydrous hydrochloric acid. So you can presume a little bit of water. You can also use another molecule of substrate. Either would work in this case.
And so, sorry, like where would it go? On the tertiary?
So in terms of elimination, if we had to choose between these two protons, the alpha proton is easiest to deprotonate for elimination.
Okay.
Yeah. So would you be able to show that elimination step from this alpha position? Yep, so we deprotonate our alpha position and eliminate, and that gives us our desired cyclopentenone product. So just to reiterate, when we treat this substrate with hydrochloric acid, we protonate our alkoxide ion and generate our alcohol. From here, we further protonate our alcohol with additional acid to yield an activated leaving group, in this case, water. From here, we can deprotonate our acidic alpha position and lose water to generate our desired enone product. Does this mechanism make sense to everyone? Does this process of drawing out the mechanism for an intramolecular aldol condensation reaction make sense? Perfect. Any other last minute questions before we wrap up today's lecture block and archive today's recording? So with that, we'll archive today's recording.